briefly introduce the second day of the workshop. Let me get my slides, which are here. And yeah, that's what I want to share. And I'm going to go in slideshow. All right, welcome everybody. A reminder that Rubin, this meeting, as all the other Rubin Observatory meetings and Rubin Observatory activities, adhere to the principle of kindness, trust, respect, diversity, and inclusiveness. You have signed the code of conduct when you signed that to participate to this workshop. If you want to review it, please, you can use this QR code or the link in the slides. You can also obviously access it from the workshop website. And if you feel unsafe at any time, or if you witness or experience violations of the code of conduct, please send an email to our OMSPA person, who is Steve Ritz, for this workshop at the email address sritz@ucsc.edu. I want to show you, I want to remind you, where is my slides are going already too fast. Here we go. Maybe they're going slow. They're loading very slow. Sorry about that. The hosts of this workshop are Lynn Jones, myself, and Peter Joachim, as well as all of the Survey Cadence Optimization Committee. The Survey Cadence Optimization Committee, I will show you the members in a second. Before that, let me show you the agenda. We are on day 2. Today we'll have presentations from the 3rd active task force of the SCOC, which is the Milky Way Active Task Force. And we'll talk about template creations in year 1. The speakers respectively will be Jay Strader and Rachel Street from the SCOC and Eric Belm from Rubin Observatory. Then we'll have a break. And after that, we will have a community-focused session where we hope to hear from you about your activities, concerns, hopes, wishes for the survey strategy. I posted on Slack a request to upload the links to your slides for this community contribution session. Please put the link on the thread in Slack, and I will later on upload the slides on the website of the observatory of the workshop. As I did for yesterday. So what you see here grayed out is the activities from day 1. And also there's links now on the agenda page on the workshop to the videos of day 1 in full. It's split into 2 videos. That's the full day, as well as on all the slides that were used. The videos are uploaded on the YouTube channel of Rubin Observatory, which hosts all of the videos relative to the observatory, including videos of workshops. So take a look at the website and don't forget to like and subscribe. And I also wanted to add a very quick reminder. This is your Survey Cadence Optimization Committee. The current members, actually, let's look at briefly their name here, as well as the survey strategy team, which supports the SCOC by producing the simulations and running the science metrics against the simulations and helping us understanding how the science metrics perform. I also want to thank the past members of the Survey Cadence Optimization Committee, whose names you see here, and I see some of you in the audience, and I'm very glad to see you again. And let me remind you one more time, the activities of the SCOC are held in a transparent fashion. The SCOC meets roughly once a month. We have liaisons into each science collaboration. The job of the liaisons is to establish and maintain bilateral communication, so to tell the science collaboration what we're working on, to ask the science collaboration to supply us with things that we might need, such as metrics or scientific insight, and also to listen and hear the complaints and the concerns, hopefully the concerns and not complaints, of the science collaborations, and bring them to the SCOC for discussion and consideration. We also have monthly office hours, and we post about our activities regularly on community.lsst.org, which is the Rubin Observatory Forum. This includes posting minutes from our meetings, as well as announcements on our progress and let me just remind you what community.lsst.org is and how it works. So this is a forum. So think about something Stack Overflow-like. You can post questions and everybody can see them and answer them and contribute to the conversation. I heard from some of you that they hadn't heard about some of the things that we presented yesterday, and wanted to highlight that really the content of the presentations from yesterday, the discussion about the throughputs, the changes in the throughputs, the analysis of the scientific metrics against those changes, those are available on community.lsst.org. Lynn had kindly posted the version 3.3 simulation, the slides that describe it, the notebooks that run the metrics against this simulation and look at their output in November. And also, if you subscribe to this topic, the survey strategy topic on community, you conveniently get these announcements in your mailbox, in your email. So you can see on the left, the post from November, on the right, what ended up in my email, in my inbox for the update to the Rubin Sim software. And that includes the announcement about the changes of throughput. So please stay in touch with us, keep up with us on community, keep up with us via your liaisons, and also contact us at any time. We are always very happy to talk to you and hear from you. And with that, I think I want to pass the microphone to the first group to present, which will be the Milky Way group. And I think that's Jay who'll share the slides.
Yep.
Wonderful. Thank you, Jay.
Okay. Can everybody see my slides?
They look good.
Great.
Yeah, it looks good, Jay.
Perfect. Thank you. All right. So I'm going to be talking today about preliminary results from the Milky Way task force. I want to stress these are preliminary. The task force has reached no final conclusions, less conclusions that have been endorsed by the SCOC. So keep that in mind. This is a task force chaired by myself and Rachel Street, and has a number of members that are both from the SCOC from a variety of areas, as well as community members from various science collaborations. You can see all of the names there. So we got a little bit of this context if you were here with us on Wednesday, but why does this exist? Right, if you had been following along to Rubin for a number of years, you know that the original plan for the dense regions of the galaxy, it was basically an afterthought, right? It was like, all right, we're going to do this big survey. We're going to have these goals. The Milky Way was mostly focused on doing halo science, not so much science you could do with the dense regions of the galaxy. And really, in subsequent years, people said that wasn't a very good idea. And right as the Rubin became instantiated as a project, and people from a wider variety of science areas than those who have been working on the project for 20 years or more got interested, we've been working on fixing that. And the reason that I'm on the SCOC at all was I wrote a white paper a number of years ago arguing that we needed to do a lot better job in the dense regions of the galaxies. I'm not the only person that said that. Many people felt this way. So that's why we're here today. And so there have already been very substantial changes in how the dense regions of the galaxy are covered. So on the left side of the slide here, right, you can see that the dense region of the Milky Way, right, had very few visits, whereas the part of the plane that wasn't less dense had wide, fast, deep-like coverage. And there was also this wide area around the Magellanic Clouds and the South Galactic Cap that had very little coverage. And now in the one on the right, which is the version 3 of the baseline, you can see that things are now quite different for the Milky Way. So now we have many more visits in the dense region of the bulge, many more visits, although not wide, fast, deep type cadence throughout the whole plane. We have improved coverage of the Magellanic Clouds right down at very low declination. And so we've already come a long way. So that's great. We can't go as far as many people would have liked us to go. And so, for example, it is not possible. There just aren't enough visits in the 10-year LSST to actually cover every part of the galaxy that might be interesting at wide fast deep like Cadence. There literally just aren't enough visits. We wouldn't meet SRD. And so the question is, right, how do we get the best science out of the visits that are available to us? And so that's the goal of this task force. And we're really balancing two things here, right? One is that, right, we want to have a legacy survey, and right, having things that are as similar as possible from place to place has certain advantages. But we also think it's very likely, and in fact, right, the metrics bear this out, that by making some changes to exactly what filters are used and what places, how frequently we visit various cases, we can amp up some science cases that are going to be important to the whole scientific community. And that's right. That's what this task force is trying to do, is figure out what those things are. So the baseline that has previously been adopted, the reasoning for the changes that were made between earlier ones and that ones, are all in the last SCOC report, which has been referenced a number of times already in this workshop. If you've never read that report, it actually goes into quite a bit of detail about why the choices were made that were made. And so it's actually a good starting point for getting yourself acquainted into how we got to this current spot and to what the things are that we're currently optimizing. But that report discusses that we basically made a decision to divide the non-wide fast deep portions of the Milky Way. And by the Milky Way, I mean the dense regions of the Milky Way, right? Obviously, the Milky Way halo is covered at wide fast deep cadence, right, over very large areas of it. And in fact, right, that's one of the pillars of Rubin science. So given the impossibility of covering all of the dense regions of the galaxy, we had to make a decision. And the current baseline divides the dense regions of the galaxies basically into three areas. So we have a high visit Milky Way. And so in the high visit Milky Way, that's the area here that you can see in the version, which is the greenish areas. These are the areas that get a lot of visits. So this encompasses a very large area around the bulge, whereas another large area in the dense regions of the galactic plane, which you can't see quite as well in this equatorial, but I'm going to flip it to galactic coordinates in just a second, and you'll be able to see it quite clearly there. And then surrounded by this much larger, about a factor of 3 larger in area, low visit galactic plane, which received still substantially more visits than it had received in the original conception of the LSST survey, but not as many as wide fast deep. So that's this paler purple color. And then down at the very bottom, we have many increased visits around the Magellanic Clouds. Those are going to get about the same number of visits at wide fast deep. These are just small areas around the clouds. And then this south celestial pole that originally had minimal coverage or no coverage at all, but now it has some coverage, primarily for doing science cases looking for dwarf satellites and other science around the south celestial pole. The percentages that you see listed there are the current number of visits in the total survey, 10-year survey, that are going to these various areas, which are sometimes called mini surveys, right? That was the term that was used on Wednesday. And so everything that we're doing here is talking about taking these numbers and just moving them around, but we're not taking any visits from wide fast deep, the deep drilling fields, any part of the survey as part of this optimization process. All we're doing is talking about how is the best thing to move things around within these areas or between filters, adjusting cadence, things like that. Here is that same version 3.0 baseline, but now I've shown it in galactic coordinates. You're seeing the galactic bulge right there at the middle. And then you see this much more extended in longitude region of the galactic plane, right around a galactic latitude of 0 that is extended over quite a wide range in longitude that is also receiving very high cadence of visits. And then this larger dusty plane area that surrounds the bulge and plane and then goes out to much further galactic longitudes, right, almost to the anti-center. And then that sort of smoothly joins up or hits the north ecliptic spur on the other far side of the galaxy. And this is the part of the survey which is being done primarily for solar system objects. And you can also see now, rather than being at the bottom, the south celestial pole is actually sitting here sort of in the middle of galactic coordinates, and the little cuts that you see out of the bottom of it, those are the high visit areas for the Magellanic Clouds. And so what this task force is doing is, how can we really refine the apportionment of these visits that are being devoted to the dense parts of the galaxies in location, time, and filter to get the best science return? So this task force was instantiated by the SCOC, and the goal is to provide input to SCOC discussions, basically to answer the remaining questions that were left by the last report that I mentioned earlier. And the official charge is that we're going to have activities that at least cover what the final design of the footprint is, so where we're going to observe. Are we going to roll in those areas, that is, do more visits some years and fewer visits other years? And what are we going to do in the clouds and South Celestial Pole? So those are the things that the task force has taken on. So I'm going to justify point by point which are the simulations that we are doing as part of this task force to evaluate to make potential changes. So we'll go through these one by one. So the first one is rolling. And right, many of you may know that, right, the decision has been made, right? The current recommendation is that over wide, fast, deep, there's going to be rolling. And what rolling is the thing that results in these stripes in declination here, which get more coverage in some years and fewer coverage in subsequent years. And this substantially improves metrics for a number of transients, most prominently type 1a supernovae, but certainly others as well. So, right, you could guess that there are temporal science cases in the bulge and plane that, in principle, might benefit from having higher cadence, right? We aren't probably going to have type 1a supernovae in the bulge and plane, although obviously that'd be very exciting if we did. But there are other, you could imagine other cases for which that might be useful. And so we did two different simulations, one of which added rolling to the bulge, which was consistent with the manner in which rolling was done in wide, fast, deep. And the other was in doing it in both the bulge and the plane. And so, right, you're seeing here what the rolling is, but not in the bulge and plane. So you can imagine just extending this rolling to the bulge and the plane. That's what the simulations did. Another one, which I'm grouping under the heading of rolling because it involves moving visits around in time, is taking advantage of the planned Roman survey of the bulge to improve the microlensing measurements that are possible by jointly basically observing some fields with Rubin and Roman simultaneously, as well as moving some of the visits around in time so that in the off seasons when Roman isn't looking at, you can get improved micro lensing measurements. So we did a simulation which basically moved around a small number of visits onto this onto this projected Roman bulge field, which basically should, right, ask what is the effect if we move around some of these visits, and we just roll basically not over larger of the bulge with the plane, but essentially just this field for rolling. Now, obviously, we don't know exactly when Roman's going to observe, and there are a number of different ways in which you could instantiate such a simulation, but we picked one and simulated it just to get a sense of what the results look like. The next thing we looked at was the footprint. And one thing that was clear from the last baseline of the footprint, which is that as we moved around these visits in the high visit and low area of the bulge and the plane, one particular example of that survey had been doing pencil beams at various points in galactic longitude in the dense regions of the bulge, and then basically we blobbed those together to make a more extended consecutive area. And in the version that we ended up in the last baseline, one of the blobs basically got left out on its own on the other side of the galactic bulge. And this is quite high air mass observations, right? So these will all be positive declination observations. Whereas on the other hand, you see that there's a bridge on the other side of the galactic bulge, which is basically preventing a continuous strip in longitude and observations that would tend to be at lower air mass, and right, hence give better data quality. And so we did this footprint, which basically took this blob, and so this simulation was called no blob, and redistributed the visits to get rid of the bridge to allow you a nice long connected strip in longitude that's still giving you a very wide range where you have very dense coverage along the galactic plane, as well as to smooth out some of this other edges of the bulge. So you have a very nice, large, contiguous area where you're getting very nice survey coverage. So that was the simulation. The next set of simulations we did is on the filter distribution. And so in the baseline distribution, the filter distribution that we currently have is not exactly the same as in wide, fast, deep in terms of the distributions between the fixed filters. But it's clear, but it's still not clear that the actual filter distribution that we'd done in these areas is exactly the same, right? The motivations for doing a certain filter distribution, wide, fast, deep, right? A lot of those things. So for example, what the total depth in the Y band might be, or the total depth in U, or needing certain temporal sampling of some filters, right? A lot of those considerations don't apply in the bulge. And so the question is, for the science cases that are most crucial for the bulge and the plane, could we do better if we moved some of the filters around? And in principle, the filter that it most seemed like the science case was maybe not as strong for as many visits on wide fast deep was the Y-band filter. And so Y-band doesn't really give you that much of an advantage in extinction versus the Z-band in almost all situations. It's less deep. The co-added depth isn't what matters across large areas of the bulge and plane because, right, you end up being confusion limited. So it actually matters is what you're getting in terms of the offset, the temporal variation. And so we tried two different simulations to try to get at this idea. So one of them was to redistribute about half of the visits to a combination of several other filters that didn't have as many visits. And that was doing it in both the bulge and the plane. And then there was a suggestion from some of the people that are interested in variable objects in the plane, especially young stellar objects, which are predominantly found there, to redistribute some of the visits from U, Z, and Y to try to get not quite wide, fast, deep like Cadence in GRI, but something closer to that to see if that can make a substantial difference in the science output. So we had those two simulations. Got a little delay in my slide coming on here. Okay. And then we also have the South Celestial Pole and Magellanic Clouds. So I'm showing it to you in galactic coordinates here. You can see I've just put a big dash circle over the area that we're talking about, the South Celestial Pole and Magellanic Clouds area. And so the scientific goals in the South Celestial Pole are quite different, right? So we're not doing a lot of the wide, fast, deep goals, right? We're not, probably looking for, how deep can we go, right? All of these observations are necessarily occurring only at high air mass. However, we know the South Celestial Pole is important for scientific goals. For example, right, we probably think that there's a lot of dwarf satellites associated with the Magellanic Clouds that are found around the South Celestial Pole. And this is actually maybe one of our best ways to figure out how galaxies are formed as a function of host galaxy stellar mass. So this is very important science. But if that's what you're going to want to do, right, probably it doesn't make the most sense to use exactly the same filter distribution that you use in wide, fast, deep. So we proposed a couple of simulations, which were led by the people on the task force who are really interested in the Magellanic Clouds and South Celestial Pole science to move some of these filters around, one just in the South Celestial Pole, and then the other doing a slightly filtered distribution of the Magellanic Clouds to see what effect this would have on the science goals. So those are all the simulations that we proposed for this. Now I'm going to walk you through the preliminary results on the basis of these simulations. Obviously, right, we're only here for a short time. It's not going to be possible to walk you through very large numbers of metrics. So I'm going to be limiting the metrics that we're looking at for this talk, but right in the final report of the task force, we'll talk about the many larger numbers that we looked at. This is a plot sort of like some of those that you saw on Wednesday, which is showing the fractional difference in what we typically call the SCOC metrics. So this is a set of metrics that the SCOC selected in consultation with Lynn and Peter to just get like a quick overview of changes that might be made and what they would do over a broad range of science cases. This obviously isn't comprehensive, but hopefully it represents a broad range of science cases. You can see I've selected here the effect that you see of the different simulations that we ran. So those are all along the bottom of the slides here. The ones in dashed are these rolling simulations that we talked about. And what you can immediately see is that for most of these metrics that I'm showing you, the rolling simulations don't do anything. But for ones that are specifically that we know are going to be important for bulge and plane science, it's very bad. And so you see substantial decreases in both this microlensing metric, which is just a special one, but right, there are many other microlensing metrics, as well as what the metric for early detection of X-ray binary bursts. But you can sort of take this to be a general stand-in for transients that happen in dense regions of the galaxies. The XRB metric sort of looks like what those things look like. And you can see rolling is bad for those, but you don't get increases in other metrics such that there's a real trade-off here. To some extent, this isn't really a surprise. There were previously in much older versions of the simulations, experiments with rolling over the dense regions of the galaxy. And that also found that in most cases, right, it was either neutral or somewhat bad or very bad, depending on exactly how it was done. And so preliminarily, what the task force is saying is we do not recommend rolling in a wide fastidioid-like manner over a wide area in the bulge or plane. This is showing specifically the microlensing metrics, and now not just looking at that 20 to 30 day time parameter, but here a much larger range of time parameters and looking at ones that have very well measured things. And you can see you basically have neutral, bad, or extremely bad effects on the metrics in these two rolling simulations, where there's only one metric, which is very high measurement over for a very small set of parameters for this. So again, this is just consistent with what I was saying on the previous slide. Now looking specifically at the Roman rolling simulation, that is on this Roman central bulge field, redistributing some visits so it's visited at a higher frequency, especially when Roman itself is actually observing the field. So what I'm showing you here is a plot of a specific year, right? So you can see it's between days 1,278 of the survey to 1,643. So this basically encompasses a time where under the current Roman plan, Roman would be observing, and so Rubin is observing at the same time. You can see that the number, right, you see the normal GDFs there in yellow, as well as the strips as part of normal rolling that are also being visited at high cadence, and then this field in the bulge, which during this time period is also being visited at high cadence. So you see that little yellow spot there in the bulge that I've done with the red circle. So that's the effect that it has. And what we see is enormous increases in a lot of the micro lensing simulations. I'm not showing the X-ray binary metrics here on this plot. That also goes up as well. And there's basically no or minimal negative effects on other metrics because the number of visits that are actually being moved around for this is very, very small. And so with this very small moving around of visits in time, we're getting a very large positive effect on a lot of these microlensing metrics. In some cases, sort of like 50% increases. And at this stage in the optimization progress, those, especially for small changes in the visits going around, are quite uncommon. So it seems like this would be very positive. And so even though we don't yet have an exact recommendation, we recommend that some version of this should be adopted depending on exactly when Roman goes up, exactly where its fields are finally. But we want to cap it at the number of visits that we're talking about doing it for this thing. So not devoting substantially more visits to it than this. But it seems like this is something that could benefit a lot of science for a very small redistribution of visits within the bulge. Looking at the footprint results, so this is on the left and the right map showing what happened when you took that blob and used it to just redistribute those visits, not just in time, but in space, so that blob visits those high air mass, high declination region, instead fill out the bulge, and they make this beautiful, nice continuous stretch in galactic longitude that goes for a very, very long ways. If you actually look at the metrics for this, what do you see? You see almost no changes at all because the actual number of visits involved in this is not very much. But right, it seems clear there are advantages to having this long strip as well as observing at lower air mass versus preferentially at higher air mass. So currently we're recommending this revised no high blob footprint. Filter balance. And so you can imagine many ways of redistributing the filter balances, right? I talked about the ones that we are actually doing in this specific case. And compared to the other simulations that I've talked about so far, these filter rebalances are much more of a mixed bag. And so we see some metrics regarding the galaxy that go up a bit, some that go down. These filter balance changes don't really substantially improve the young stellar object metric, which was one of the goals of looking at the simulations, especially the one only in the plane. So you can see here, right, the fact that you basically can't see colors very well in these regions, indicating the metrics just aren't changing very much. Even if you look specifically at the microlensing metrics, which you might expect to depend, if you take some of the visits out and stick them into the ones that microlensing is more dependent on, you might expect changes. You barely see anything that's significant there. It just doesn't seem like it is matter varying others. And to the extent that they are significant, you see a few go up and a few go down. If you look at other things that might also depend on what's happening in this area, so for example, we looked at stars metrics. We also looked at solar system metrics, since the ecliptic, of course, goes through the bulge. We're just also not seeing substantial changes in most of the metrics. And so the conclusion so far on the basis of this is that we're not really seeing changes. What does that mean? I think it means we don't have the right metrics. And so, if you compare the number of visits that are going into U and to G, and G even, which is common in very many metrics, is going up by about 15% of the visits in the bulge, I would expect this to affect some bulge science meaningfully. And so, I think the existing metrics just aren't sensitive to these changes that we're making, or we're inadequate, We haven't done a good enough job in the metrics that are sensitive to these filter changes. And so that's a problem. That's something that we have to address, and that's going to end up being one of our main recommendations. Looking specifically at the two different simulations that we looked at, the plane or the bulge and the plane just isn't making changes much at all. And so it's not clear to us that there's a really motivation to only look at the plane separately. So we think that we should be focusing on, are there filter balancings overall that we should be looking at across the whole dense regions of the galaxy? And that's where we want to focus for future work. The Magellanic Clouds and SCP, I don't have anything to say about that. The analysis is ongoing, so we haven't reached any conclusions about that yet. Like I said, the central goal here is we want to improve shallow population science in this region, especially detection of dwarf satellites around the clouds. And so I would imagine these changes would affect that in some way, but we just don't know what the results are yet, so I don't have anything to say about that. This is my last slide. So if we didn't do anything about the filter balance in the bulge and the plane, that's not a problem. It's clear from looking at the metrics that we do have that the survey that is currently planned for the bulge and plane is going to be amazing. It's going to do great science. However, I think it's possible we could even do a little bit better, and so that's what we're talking about. We're talking about optimizing, not, is this mediocre? We're talking about, can we make it just a little bit better? And so this is really a clear area where we need more community input to develop metrics. So if you, and by I literally mean you, if you listening to this, have science that depends upon what we are doing in the dense regions of the galaxies, we really need either math metrics or other simulation-based analysis that capture the effects of these filter changes in the sciences. I don't believe that your science does not depend upon how many visits we're doing these filters. I know that it does. And so, that's an area where we've fallen short. It has to be dealt with. Again, I don't have anything to say about the SCP and Magellanic Clouds at the moment. And just on a timeline, so we're mid-January. Our goal is to have a complete report from the task force and have a final report that we deliver to the SCOC by about 3 months from now. So about mid-April, and then the SCOC will consider it, and then that'll roll into our next recommendation. So that's all I've got.
Thank you, Jay. This was y'all have done an amazing job on this task force. Thank you so much. And thank you for the survey strategy team. They put in a lot of simulations to support this task force. Thank you. This is extremely appreciated. And I don't want how much work this takes go unnoticed. We have time for a few questions, I think. I saw some conversation on the Slack, but maybe let's take Natasha.
Hi. So thanks, this work is awesome. I just had a quick question with regard to the rolling. Is are the Magellanic Clouds included in the wide, fast, deep rolling, or in the galactic bulge plane definition of rolling? As in the current strategies, are they being rolled or not?
I think in the current strategy, they are being rolled. Is that correct? That could be wrong. Somebody should correct me if that's not true.
Okay, so I guess it would be interesting.
Yeah.
Okay, so it would be interesting to, I guess, figure out if the science in those is closer to the galactic plane science, if we want to adopt a similar rolling strategy for both of those.
Yes. So certainly it's that in the clouds themselves, I would expect the scientific cases to be closer to what you see in the bulge and the plane. But of course, it's affecting fewer other things. So, right, if you change something in the bulge, right, that does change solar system, that changes the other thing. If you change the cloud, that changes, right? They are themselves, right, their own thing. They should be considered that way. I really can't think of a reason that in the South Celestial Pole, right, we would, what you get out of rolling would be, important for most of the science cases.
Simona, you have your hand up. I just want to flag that in about 3 minutes, I want to move on to the next session. So just keep.
Okay, we can discuss this also later, actually. Is it something that I will present to the SCOC as feedback from the Galaxies collaboration? I'm wondering, I mean, you mentioned that increasing the visits in the U-band of 30% would help some science cases. And I wonder if you have done some simulations about that, especially, I will say it later also. IZ galaxy photometric redshifts or cataclysmic variables and other active sources in the Milky Way, metallicity, the Milky Way, reddening, etc. And I mean, we don't have to discuss it now because we only have 3 minutes, but it will be interesting to know it when there is the general discussion.
Yes, right. Some of those things, right, like what's happening in the halo, right, is not this task force is not looking at the effect of U-band on halo science, but that is something that affects the Milky Way and is obviously crucially important for a wide range of science cases. So I agree with you.
Yeah, and this was flagged as one of the topics where possibly we would need a metric, which we don't currently have. So if anybody feels like they have scientific insight that can guide us on what metrics to build, or coding insight that and can spare some time to write the metric, the SEOC will much appreciate it. We are tracking down that case, and we are going to include it in our considerations about rebalance and potentially U-band observations. And Rachel, as co-chair of this task force, I just want to ask if you have anything to add in the last minute.
Hi, everybody. Thanks for the opportunity, Fed. In the interests of time, I've posted my comment in the Slack. So I think it's probably best to move on. I don't have anything to add. Jay, the presentation was fantastic. Thank you.
And I want to stress to everyone, the most important person in getting us to the current spot we are in terms of the bulge in the plane has been Rachel's efforts in coordinating the efforts of a much larger collaboration. So thank you, Rachel.
Yes, I want to second that. Rachel has done a fantastic job at coordinating the TVS and the Stars Milky Way local volume collaborations to come together on this topic. Thank you, Rachel. Your input has been invaluable. Thanks again to the task force. I will talk perhaps more about related things when we get into the community sessions. So let's move on now, and we have Eric Belm from the alert team to talk to us about work on template construction.
Hi, everyone. I look all right?
Yes, it does.
All right. So I was asked to come and say a few words about template generation, especially in the early survey. I serve as the alert production science lead for data management. This slide is from Keith Bechtel, and it is schematic. There are no dates on here, and I think it's also evolving as the summit schedule changes and plans for ComCam change as well. But I think the takeaway here, this is sort of walking us through the process from starting first photon with the main LSST camera and into the commissioning period, the start of the main survey, and then its continuation. And in the bottom are various sort of data previews of commissioning data, as well as the eventual LSST data releases. And the thing I want to highlight here is that some of the earliest science that the community will be able to do with the LSST survey is going to be driven by the nightly real-time alert production. So that we expect to start sort of late in the commissioning period and near the start of the main LSST survey. And so obviously everyone, I think, is extremely excited to start writing science papers with LSST. And so for many science cases, alerts are going to be the place to start with that. The constraint is that alert protection relies on the existence of co-added template images. And in data management, we use a scheme of tracks and patches, which are these defined sort of squares on the sky that are sort of locally flat. And we co-add images into them and then use those as new science images are taken as the template or reference image. There's no constraint on what can make a template. You could use a single image for it, but it does have to be sort of worked into this overall sort of coordinate framework. So one thing that's a little different about Rubin relative to sort of other surveys that folks might have experience with is that Rubin is heavily dithered both spatially and rotationally. And so they're the things like chip gaps and dithers and stuff mean that it is not it's a little more complicated to make that template once you start sort of piling up actual survey images. Nevertheless, the relatively high fill factor of the Rubin camera means that even with the relatively few images, you will cover the sort of square area on the sky, modulo sort of various edge effects of different edges of the camera and so on. We do have to worry a little bit about discontinuities in the PSF as we think about image differencing, but I think that's something that we can handle. The other thing to think about, so when we're thinking about making a template, we would like to have ideally lots of input images, which we will sort of later in the survey, so we can select the very best ones. But we think that we need at least 3 for a few reasons. Among them is that it allows us to reject some classes of artifacts. You can see here sort of more naive co-addition methods. And then on the right, a sort of safe flip algorithm that we have implemented in the stack that lets us reject some of these larger transient features that are not corresponding to astrophysical variability and get a cleaner co-add. So that requires a number of images. Also, as we add images, we improve the noise properties, we reduce the noise of the co-add, improve the sensitivity of the difference images, and increase discovery capability. So, and finally, the better seeing the template is, that also helps increase the number of alerts we get. The other constraint that we have to think about is that we want to, as much as possible, avoid repeated changes to the template, because every time you change a template, you change all of the sort of flux baselines for variables. And if you have a supernova, it changes the sort of, there's contamination in the template, which complicates your discovery and certainly also use of the light curve. So what we'd like to do is make our first templates as soon as we can, but then keep them fixed until the next annual data release, DR1. So the plan, which we have been advertising for some time, is we'll do what we call incremental template generation early in the survey. This is a little outside of what the original plan for LSST was, but which would have templates only made in large-scale data releases. But our plan is that as we take images in commissioning and the early survey, we will regularly and continuously assess if we can make new templates with some of those images. And when we are able to, we'll make a co-add, vet it, look at its properties, make sure it is not going to create artifacts and problems, and then deploy it to production. So then when the next time you have a visit to the sky that overlaps the area with the new template, you'll get alerts, and science users can do science with it. So again, the thing to emphasize is once we make the template, we won't replace it until DR1. I won't walk through this in detail, but I think it turns out not to be as big of an issue as I expected, and I'll describe that in a moment, but there is at least empirically a little bit of a trade-off here between getting templates earlier, which lets you start science faster, discover and follow up things that you couldn't otherwise do so, versus sort of some metrics of template quality. As you gather more images, you can go deeper, you can select better seeing subsets, you might get better artifact rejection and so on, but at the cost of delayed science. And so thinking about how that trade-off would work in practice, I think is a question that is before us, but I think it turns out to be a little less of a concern than I'd expected, as I'll describe. So even with relatively, what I would say are fairly coarse cuts, so requiring just 3 images in a template, and the seeing and depth being less than a 50th percentile of the overall distribution, you can see that relative to the first visit of the night, you pretty rapidly, within a month or so, start getting about half of the sky area with templates. And so there's, it's a gradual ramp. This is by filter, and again, time since the night of the first visit, but you're pretty quickly building up template coverage across the sky with these relatively coarse cuts. And this is that same, basically the same view spatially showing the color scale is showing the night the template was created. And mainly the thing to take away from this rainbow is that, of course, not all areas of the sky are visible throughout the entire year. And so there already is some degree of delay that's necessary before you can create a template. One way of thinking about the quality of those templates is thinking about transient science specifically. And this is a little metric that I put together that if you think about a difference image sort of probing a cone of space, the sort of volume that it surveys is proportional to the limiting magnitude of the difference image, and the number of alerts are going to be proportional broadly to the volume that you're surveying. And so you can ask, if I have a deeper template, does that let me get more alerts versus a shallower template that is available sooner? And so the plot on the right is showing 2 examples. So the blue is, again, that 3 images with a 50% seeing and depth cut, and the orange is 5 images with a 25% seeing and magnitude cut, depth cut. And you can see that far and away the shallower, earlier template strategy gives you a large volume more alerts for transient science. And so that suggests pretty strongly that we would prefer to sacrifice a little depth and get the templates sooner and start science sooner. You could also worry a little bit about, well, if we're selecting just the top half of the seeing distribution, are you going to get a bunch of cases where the template has pretty gnarly seeing relative to the science, and which is not ideal for difference imaging? And that turns out also not to be the case. We're using inverse variance weighting in our coads, and so this distribution is just showing the difference between the science and template seeing, again, for that 3-image selection. And the vast majority of the differences have better seeing in the template, which is what we want. You could imagine that you could adjust the survey strategy to try to influence template generation. There's, I think, a little bit of a trade-off there, because if you're focused on making new templates, that means you're not observing areas where you have templates, you're not getting alerts. And so there's a little bit of a trade-off between, exploring and exploiting. That's a science-driven concern for the SCOC. Similarly, I know there are some concerns or questions around whether adjusting the year 1 survey strategy impacts static science long term, which I think, again, is a question for the SCOC. I think the point that I want to say with my data management hat is that we will make templates with whatever data is available, and it's not strongly influenced by how those images are taken. So it's not a technical concern from the data management side. Where we're going from here, I think if there is an appetite for looking at adjustments to the survey strategy, we certainly could look at the impact of expectations of template and alert availability. The plots I was showing are all math metrics that are not totally merged yet, but could be. And then obviously there's a fair bit of hands-on work for the data management team in terms of looking at real data, precursor data, commissioning data, making sure we have the right quality cuts and sort of infrastructure for vetting the templates once we make them so that we're satisfied they're of good quality and putting them into production. So this is where I'll close. We're very excited about the time domain science that will come from Rubin. And by making templates incrementally early, we'll be able to enable early alert science. And I'm optimistic that that will come on very quickly once the survey starts. So thanks.
Thank you so much, Eric. This is it's really nice to see all this coming together. We have the floor open for another 20 minutes or so before our break. So yeah, ask your questions. And Igor, I saw you put something in the chat about Stephen Bituon, the hand raised. So Stephen.
Sorry, put my camera on. Can you hear me okay?
Yes, thank you for being here at relatively late hours.
You're welcome. Yeah, it's pretty dark here, but it's not so late. Hi, thanks, Eric. That was great. Your thoughts on the deep drilling field strategy, because that's somewhere where we can get going really quickly. In fact, it won't take that long to build up templates in the DDFs. And even the science that we would do, the transient science we would do, could get going really quickly, and there'd be great test fields to test things from start to finish.
Yeah, absolutely. I totally agree, Stephen. The DDFs will produce templates quite quickly, very naturally. In fact, there I think we almost want to. I won't say take our time, because that implies a degree of slowness, which we don't want, but. There, I think we have the luxury. We'll have so many images very quickly that we can be a little more choosy and make sure that those are really solid templates, so that as you said, that those can be a focus of early exploitation. And my understanding of the commissioning planning is that the DDFs will certainly be hit already in commissioning, so we should be able to form templates from them probably even before the survey starts for whichever are visible at the time of the commissioning.
Thank you. Excellent. Meg?
So I guess I wanted to raise the question that this is a lot more pressing in time compared to things like some of the uniformity, because that's in year 5, right, that you might stop rolling. But this is, going to happen at the end of 2025. And so I think there's a lot of things that are in here that are quite important. It's not clear we have all the metrics for this. And so I guess my question or request to the SCOC is, you've stood up task force for other things, but are you going to stand up soon a task force for this? Even if you are not going to make decisions soon, allowing us as a community a way of being able to feed back to you simulations to make, because these trade-offs are important. And particularly if you're going to be applying to do science in the first year of LSST, I can easily see proposals being shot down because they go, we don't know what template generation looks like, so you might not be able to do that. I know I've gotten proposals shut down because they said the schedule was going to move, so we don't think that you're going to be able to do the science in the time frame. And so I guess I would just like to ask, is in the SCOC schedule, is it possible to spin up a task force on this, even if decisions are not going to be made very quickly, but to start that discussion? Just like some of these other areas, to me, this seems just as important as these other levels of things that are being modified, but in the time scale, it's actually sooner, especially if people are planning to think about follow-up in other facilities and other proposals like JWST to be applying for.
Thank you, Meg. At the moment, the SCOC is planning to treat this as a SCOC-wide decision and not a task force. You should not be reading into that the fact that we think that this is less urgent or less important than any of the other topics. It's just something that we think is better suited for everybody to contribute, since it's of broad interest to everybody on the task force and everybody has insight compared to other more narrow topics. And community contributions are always welcome. I wanted to also flag that and let everybody else know that some of the science collaborations have provided already input. I know that Solar System will talk about it. I believe we'll talk about it in the community session about their work on templates at the moment, but also the Solar System Science Collaboration has produced a white paper some couple of years ago, as the TVS and the desk produced an internal document that was shared with the SCOC and with Rubin on their thoughts on constructional templates. And all the other science collaborations, we would like to hear from all of you, and we want to consider all of your input. These decisions are also they're not restricted to the SCOC, but the SCOC necessarily is working with the alert production team and the early science team on all of these things. So there's a lot of people that are paying attention to this and discussing it and carrying on the conversation. If you want to contribute to this conversation and you feel like you have not yet, and you don't know how, and you're in a science collaboration, start by reaching out to your liaison and let them know, and we can see what's the most efficient form for you to communicate with us. Any other questions? I'm gonna take a look at the chat. Anything that is in the chat should be said out loud. Lynn, Peter? Oh, and let me add actually to the answer that I was giving earlier, that we were just talking about introducing metrics that we can track together with all the other metrics that we regularly run on all the simulation that represent how fast we get the template, something along the lines of at what point do we have half sky covered in templates, or what is the part of the sky that is covered in templates over time. So we can continuously track this with all the simulations that we produce for other purposes. Peter, did you want to add anything? I saw you turned on your camera.
I was just thinking that our default DDF dithering strategy is to have one dither position per night. And so for the first few nights, we might want to change that and do very large dithers spatially and rotationally, sort of, after 2 or 3 sequences, then we can do a great template and then go back to our usual. And then we can do it.
Excellent. Any other thoughts? Any other questions?
I was just going to say, in terms of metrics, I think these are some of there's a whole set of early science metrics that we might want to start having a look at. So yeah, putting template generation metrics into place and other things that look at just what is the survey like at the end of 1 year is probably a good idea. So we'll start working on that.
Yeah. Meg?
So where does that fit into the SCOC schedule? Because I want to just highlight that there's been a path that Rubin Observatory has done in many different ways, where you ask us to do work over Northern Summer. And many people are funded on NSF grants and other grants to do other science because they're using their summer salary. Also, people go away. And so I worry in the SCOC schedule, you'll decide on a baseline, right, and present the draft in the summer, and then we'll be asked at that point to start doing incremental template generation when there's only a very narrow window before people have a picture, right, have to be writing their NSF proposals. And so I would just like to highlight that if there's a way to avoid doing that so that people are not spending their entire summer rushing to get year 1 incremental template metrics or suggesting things, that would be really helpful, because it's happened many times in the past. And it's something it's feedback that I hear that's especially tough at that time when it's given people are supposed to be doing other things or actually funded to be doing other science. And so having a little bit more time, right, especially if they feel like there's possibilities of knowing some answers, even narrowing phase space down, of being able to do that before the baseline is finished, because as you said, most of it's 90% of it's there. We could have some understanding at least of the phase space of incremental template generation before that. So I hear we're going to think about making some metrics and releasing them, but is there a way to codify a schedule or a include that in the draft of whatever your timeline is, the community can give some feedback on that of what our constraints are, so that we can work together on this rather than feeling like we're being at the community workshop, like feeling stressed that we have a month to basically work on and ingest incremental template designs and metrics.
Lynn, go ahead.
Yeah, thanks. So the thing is, Meg, these templates about incremental, these metrics about incremental template generation, in terms of the metric, can we make a template or not? We basically already have that from the person who is doing in charge of what incremental template generation should look like, right? This metric from Eric, which is based on the same kind of metric that you know, that you've worked on and that Jamie has worked on. So it's basically the same, but with the cuts that Eric thinks is reasonable. So I think that that's already in place. And then we can do the similar kind of thing where we only use this guy that's got that incremental template, and then we can just run all of our other metrics that depend on having a template to be able to predict what that early science is. Like basically the metrics we already have. So I guess the question is, I feel like the metrics are already there and we can run them. We just have to actually do that and get the metric from as set up by Eric. And so I don't know that there's going to be a call for a lot of collaborations. Now you have to give us new metrics. If you do have something that you want to have a metric that we're not already running, then let's start talking about that now. But I think the idea is that this actually will get looked at and simulated relatively soon. And yes, the V4 template or baseline survey is going to come out probably sometime around the PCW, I think is the schedule you said, Fred. So that will sort of be in the summer. It's true, but also it's about it's about the earliest and the latest that we can do that. So that's mostly my thing. I think that if there's stuff that's missing, this is a great time to tell us right now already. You don't have to wait until the summer.
Yeah, absolutely. If there are any metrics that respond to template creation that you have created already, more likely that you have in mind but are not being coded, let us know. We'll do what we can to turn them into code, and we'll continue monitoring them throughout. Any other questions or thoughts? Natasha?
I just had a quick question about the dithering, the rotational dithering stuff. Can you go into a bit more detail about the sort of systematics you would expect from that sort of strategy?
Are you asking us about that, or are you asking Eric about
think
that
Eric.
for template?
Yeah, I think Eric. Yeah.
I think sorry, let me see if I can answer your question. We talked about it in a couple contexts. I mentioned it just as a concern in general, wide, fast, deep, that there's heavy rotational and spatial dithering. So there's larger PSF discontinuities that we see in the template that is a little bit unusual. We have simulations of this from the DC2 DP 0.2 analysis, and it doesn't appear to be a dominant effect. It's just something I worry about with my alert production hat on. The other thing that folks raised that Peter mentioned was as we try to build templates for the DDFs, we want to make sure that we are representing the full range of dithering before we make a template, which may require some modest scheduler tweaking. But I think that's easily handled. Does that answer your question?
Yeah, I think so. I guess, is there any sort of concern if there's like PSF variations about like in crowded fields there being like weird effects on blending and crowding and stuff?
I mean, yeah, I think those are real concerns. I don't have I don't have anything feel good to say, you know, other than we are continuing to look at precursor data with the stack and pipelines, and you know, we'll certainly be taking crowded field data and commissioning to understand the state of the pipelines. But yeah, it is a worry that I have, and it's a real one.
Yeah, thanks.
Thank you, Eric, for the honest answer. We have 5 more minutes, actually more like 9, if you have more questions. Otherwise, we can break off a bit early. It goes in 3, 2, 1. Okay, we officially entered the break, which ends at, let me get it right, 10:45 Pacific time, grouping time. We will see you there, and that's the moment for your community contributions. If you could please share the slides, that would be great, so I can post them on the agenda and put them on the Slack channel, ideally in the thread that I initiated, but you know, really anywhere. And maybe let me just remind you what the lineup currently is. I do have it on a slide here. Right, so the current lineup is Solar System Science Collaboration Desk, TVS, Galaxies, Strong Links in Science Collaboration, AGN, Stars Milky Way Local Volume. If any of that doesn't sound right, if the time slot doesn't work, or any of that is a problem, please let me know, reach out to me and I will fix it. And otherwise, we'll see you at 45 past. Thanks, everybody. And I think we should start right away. We're gonna start the community contribution session right now. You've seen the schedule, so solar system science collaboration is on deck. Every science collaboration has roughly 8 minutes. SSSC asked for the contributions first and was told 10 minutes, so you're good with 10 minutes. We have a bit of buffer at the end, so don't be too stressed about the 8 minutes, but also we do want to all log off at the end of the next hour, so please keep roughly within your allotted time slot. And it's going to be solar system, and then next on deck is going to be the dark energy science collaboration. Off we go. Jamie, you will be speaking for the solar system science collaboration. Thank you very
Yes. Hi, Federica. Thanks very much. And yes, my motivation to be on time is getting my dinner. So, but if I can,
Thank you for being here in the evening. We appreciate it.
Oh yeah, no problem at all. But I'll share my screen. Can everyone see that? Okay. Perfect.
Yes, it is.
All right. Just set a wee timer for myself as well. But yes, thank you very much for giving me the opportunity to speak. Yes, I'm a member of the Solar System Science Collaboration. I'm a postdoc working at University of Edinburgh with Cyril Opatom and Colin Snodgrass, so I am very interested in everything asteroids and comets. But I've also been working quite closely with Meg Schwamb from Queen's University, and she sort of put me onto this interesting project trying to simulate incremental template generation during year one of LSST. So as a brief overview, as I'm sure we're all aware, in order to generate any alerts during year one, we need to have templates available for that particular patch of sky. The templates required to do the difference imaging, and therefore, create these alerts that will give us the science that we want to do in year one. So for example, just here is some sky maps of the latest baseline version 3.3 divided up into the filters. And you can see how each sky map, apologies for the sizes, but in general, some filters are fewer visits than other filters. For example, R has lots of visits. Some filters don't have certain regions, such as the North Ecliptic Spur. So we essentially came up with this simulation framework built within the existing Rubin Sim metric analysis framework that allows us to simulate the effects of template generation, accounting for all these different, you can just feed it your general baseline. It will divide everything up by filter. And basically what we've done so far is we've been considering how the effects of this incremental template generation impacts on the number of visits that we won't be able to generate alerts for because the template wasn't available yet, and we focus in particular on how it impacts on solar system moving object discovery criteria as well. So again, I'll just skim through this bit quite quickly, but as I'm sure we're all aware, the sky map for the survey will be divided into these tracts and patches, where a patch is approximately 14 arc minutes in size, and that's comparable in size to the sort of projected footprint of a single CCD onto the sky. And the interesting thing is if you consider patches of the sky that are that size, the number of visits across each of those patches will actually vary quite a bit. Due to the nature of the dithering of the field of view in the baseline version 3.3 simulation. So you can see here this visualization that Lynn put together, where if you have your visits dithering around, the actual counted number of visits per pixel will vary quite a bit across that field of view. And interestingly, you can start to see the sort of patch tracked layout of the camera coming through and overlaid in this figure. But basically, what did we do to try and simulate template generation? So we decided to run these metrics. We wrote our own metrics within the framework. we decided to use heel pixel sizes of 14 arc minutes in scale, so n side 256, and that's because these heel pixels that we're then measuring properties across, they're comparable to that patch size we just mentioned. And in our method, we pick different time scales for template generation. So overall, we've considered a range of different time scales from 3 to 28 days. 3 being an optimistic push in our opinion, but happy to talk about that with more people. 28 being like a sort of worst case scenario. 7 being maybe realistic in terms of how often we can expect templates to be regenerated. But basically, whenever we have a template generation night in our framework, we use the metric analysis framework to grab all the visits up to that template generation night on a given heel pixel, and then we look and see that if that heel pixel had at least 4 visits of sufficient quality. We have some quite simple template image quality requirements. I'm sure Eric went into a lot more detail about template image quality, but we just use these very basic ones for now. And essentially we say that that heel pixel would have had a template if on the previous template generation night it had those 4 visits. So then in that time period since the previous template generation night, all of those visits that lay on that heel pixel could have potentially generated alerts. And the way that we implement this into a full year 1 simulation is that we divide the whole year 1 database into cumulative chunks going from each template generation night. Anytime a heel pixel has, anytime a visit has within its extent at least 1 heel pixel with a template, we record that. So we can, for each visit in the year 1 database, we can record the total fractional template coverage. And that's what's shown in this histogram here, where not all visits will have full template coverage. And a lot of them, this spike near 0 coverage, those are mostly images that go into making templates. But then once we have those heel pixels with templates, we can then use like sort of standard metric analysis framework metrics and count the number of visits and pairs and the time between the first visit and the template creation. And then once we have our visit database with this template coverage, we can then like choose some cutoff. Let's say only consider visits that have at least 90% template coverage. We can then pass that through the solar system moving object metrics for discovery and characterization. And here's just a little animation showing side by side on the left how the baseline survey should proceed, ignoring template generation, and on the right how when you bring in the requirements for template generation, there's a time lag in terms of getting enough visits to catch up and start generating visits that can do alerts. There's also patchiness where you're not getting that full coverage. I won't talk about this slide too much, but basically this is just showing off, we can do lots of those standard metric analysis frameworks like counting number of heel pixels. I think Eric showed similar graphs here, which is delta night, which is the number of nights between the first visit to a heel pixel and when a template was available. And yeah, just total sky area and stuff like that. We can get all these summary metrics that I can like show people in a lot more detail later if they're interested. But I think this is the really interesting thing here, where if you look at this top row here, the sky map is baseline version 3.3, so assuming no need to generate templates, just the standard year 1 visit database in the R filter. We've taken a region in the North Ecliptic Spur, the Wide Fast Deep survey, and in the galactic plane, and you can see that you have nice numbers of counts for all of these in the year 1 baseline. But like in that animation, whenever you then account for you need to generate templates, things become patchier, and zooming in you can see this, and the actual difference in numbers between these two sets of images are visualized here. And in our requirements, we required at least 4 visits for template generation. And you can see that overall, uniformly across the sky, pretty much you've just subtracted 4 visits. But in some areas, there will be more visits needed to get that overall coverage and quality. And there is this patchiness that is introduced. And then, yeah, just aware of the time here. So just briefly showing the results of some of these moving object metrics. So as I said, we ran a redacted year 1 visit database through these moving object metrics. So for example, this shows the discovery discovery metrics for main belt asteroids relative to just the regular baseline version 3.3 baseline. So we're actually getting drops of, nearly 50% in terms of the number of main belt asteroids that we could expect to discover during year 1. And likewise, this is a similar figure, but instead showing how the number of objects increases over time for year 1. And the interesting thing is that, I'm sorry, I should say this is on the left for bright main belt asteroids and on the right for faint main belt asteroids. But the effects of template generation, these colored curves here, it's introducing a time lag. And yeah, that's the time that's required to get those visits. So I'll just finish briefly with my conclusions, but essentially we have developed this framework. We're going to be publishing it very soon. We want people to be able to use this. But the important thing to get across here is that I think this tool, we can then, if we have simulations of slightly revised schedules just for year 1, if we can maybe find some small amounts of additional time just to, the regions that are most heavily affected by this template generation are the regions that are already low in visits or low filters that are low in visits as well. So for example, that's why we looked at this. The wide, fast, deep is going to be fine, we think. It's not losing a huge amount of visits proportionally, whereas the North Ecliptic Spur in particular, if it's only getting, max of 12 visits and it's losing 4 across the board at least, that's one of these under-sampled regions in year 1 that might suffer. So that's sort of what we're maybe saying is, yeah, if it is possible to get these sort of simulations as soon as possible, and then we have the tools now that we can start to analyze them. But yeah, feel free to reach out to me via email or talk more in the Slack channel. But thank you.
Thank you very much, Jamie. I propose we pair up and we do questions after 2 talks just to save a bit of time in the transitions. So I would like the desk science collaboration, the Dark Energy Science collaboration on deck. I think Jeff Newman, you're going to start?
Oh, where's Philippe? Philippe was going to show
Philippe
the
is going to
slide.
start.
But I don't see him on, is he?
He was on a minute ago and I confirmed with him that he was ready. So during this transition, eating my words, if anybody has a question for the solar
Just
system
sharing my
science
screen.
collaboration. Okay, Philip is here.
Great.
Yeah, I'm just sharing trying to share my screen.
Perfect.
Okay.
Looks good.
Yep.
Great.
So Jeff, you please.
Yeah.
Yeah.
So we'll be talking about 2 topics. I'll talk about the first, and Philippe will talk about the second. So next slide. So the 2 topics we'll be talking about is number 1, synergies between Rubin and DESI 2, and some discussions we've been having on both sides. And then Philippe will talk about deep drilling field strategy. So next slide. So on the first topic, there's been a task force formed within DESC for joint discussions about how can we maximize the synergies between Rubin and DESI 2. And for those who aren't familiar, because it's really a new concept, the plan is that there will be a DESI 2 survey. This was endorsed by the P5 report, so DOE is going to run forward with it, we expect. That would run for 5 years starting in early 2028. It would look at different sorts of targets than DESI 1 has, but still with the goal of doing cosmology. The plan is the bulk of the survey would be probably equatorial, about 5,000 square degrees instead of 14,000 for DESI 1. And instead of targeting lower redshift galaxies, the intent is really to target objects at z greater than 2. So there's two key populations, Lyman break galaxies, which you need U, G, and R bands to select, and Lyman alpha emitters, which the plan is to select with medium band imaging. And then in gray and bright time, there would be spectra of stars and lower redshift galaxies as well. Next slide. So there's a couple of concerns that have come up in these discussions with DESI that I want to raise because they connect to the survey cadence we're talking about. So the first is what the impact of the change in throughput on the U-band depth would be in Rubin, because the U-band is critical for selecting these Lyman break galaxies. You need to be actually deeper in U than G or R to do this well. And also what the impact of depth variations in Rubin would be on the DESI-2 large-scale structure measurements ultimately. And so the simulations and tests are suggesting that DESI-2 would need basically 4-year depth imaging in LSST. And of course, there won't be 4 years of LSST before 2028, but for 2030 there should be, right? So the hope on the DESI side is if there's some way to do a couple of thousand square degrees in U to 4-year depth within the first 2 years of the survey, and these blue boxes are illustrating regions where that might be possible, it would enable DESI-2 to use Rubin for the U-band for the target selection through the full DESI-2 time period. So next slide. So the other concern that's come up is variations in the extinction-corrected depth of the Rubin imaging. Because for large-scale structure, for extragalactic science in general, we care about the extinction-corrected depth and variations in that depth, not the raw depth, not the number of visits, but what is the depth after you correct for Milky Way extinction. And this has, of course, the biggest effect in the U-band, where the reddening is greatest. And so there's experience on the DESI side from the legacy surveys, where they have a very similar variation in depth in the DCAL's G-band as in LSST year 2 G-band. But the difference is DCAL's had 3 visits, and LSST year 2, right, is dozens of visits in G. And the way they did that is by adjusting exposure times based on the extinction, the Milky Way extinction, based on the air mass, and based on the observing conditions. And so DESI-2, because the uniformity is a big factor, would be really interested in whether it's possible to explore some modifications to the LSST strategies that would make it more uniform. So the simplest of these would be just changing the weight in the next field selection, basically, for priority for uniformity compared to the other factors, right? There is a factor that's basically trying to bring things to the same depth, but you could adjust that weight and it would be more uniform if you do that. The next order of thing you could do is, instead of looking at depth compared to what would the depth be after 10 years, for a fixed number of visits per point in the sky, try to prioritize the extinction corrected depth, making that uniform. So you'd pick the next field that will make the extinction corrected depth more uniform, rather than the next field that will get you to the most uniform fraction of 200 visits or whatever. And so that's probably pretty simple to do in the software. It is a strategic decision, but it would make things more uniform. The next thing you could do is, how signal noise should scale with air mass in a given band. How signal noise should scale with Milky Way extinction for the extinction corrected magnitudes. So you could scale exposure times with that. And so the exposure time would vary across the sky accordingly. And then the final complication would be to do it basically the way the legacy surveys did it, and adjust exposure times based on air mass, extinction, and observing conditions. So there'd be interest, I know we don't have time to discuss this now, but there'd be interest in, are there ways to explore these range of strategies, how far could we get, and look at the impact both on uniformity, which affects all extragalactic science, as well as the DESI-2 science as well. So Philippe, I'll turn it over to you now.
Thank you. So we are also working on desk cohesive DDF strategies. So DDFs are critical for at least 3 desk probe, the photometric redshift and the weak lensing, and this is mainly for calibration purposes, to have an enough depth so as to have good calibration, and also for type 1a supernovae. And it's more a requirement for cosmology, because if you want to measure W0 and WA with a high degree of accuracy, we need to observe a large sample of IZ type 1a supernovae. So the goal of the study is to design a DDF strategy that will fulfill requirements from photo-Z, weak lensing on type 1a supernovae, and also the SCOC phase 2 recommendations. So up to now, there were 2 types of simulated DDFs, either with the uniform cadence, that is all the field were observed for 10 years with the same cadence, the same number of visits, etc. And the other possibility is the SCOC phase 2 requirement, that is recommendations corresponding to a Cosmos field with observed for 3 years with the 10-year equivalent depths to the other fields, and all the other fields were observed in a uniform way. So what we are trying to study is rolling strategies, which would be composed of 2 ultra-deep fields that would be observed at high cadence with a high number of visits, more than 100 per observing night for a few years, between 2 to 4. And 3 deep fields that would be observed with a uniform cadence and a lower number of visits. So you have on this slide all the parameters that would compose a strategy in terms of the number of visits, number of season, and also budget, etc. You can take all these numbers and you will end up with the formula that you have on the right of the slide. And if you inject in this formula the phase 2 recommendation related to the budget, to the number of deep field to observe, the number of season, etc., you will end up, in fact, with 4 parameters, which are the number of UD fields, the number of UD season, the number of UD visits per observing night, and the number of deep field visits per season. So we can try to use a graphical method to solve this, to try to design cohesive DDF strategies. So you have on this plot the number of UD visits per observing night as a function of the number of DD visits per season, and the 3 lines that you see correspond to the allowed parameter space corresponding to 2 UD fields and the number of seasons of the UD season varying between 2 and 4. So on top of this plot, we can superimpose the requirement from type 1a supernovae, which has the horizontal line that you can see here, which correspond to, in fact, to a depth up to which we would like to observe type 1a supernovae from its redshift completeness, 0.70 to 0.8. And the vertical line correspond to the requirement coming from the photo-Z and also the weak lensing. So in fact, by taking the intersection between these 2 parameter space, the requirements and the one coming from the strategy, we end up with 12 scenarios, where 3 are optimal for type 1a supernovae, 3 are optimal for photo-Z and weak lensing, 3 are a compromise between the 2, between type 1a supernovae and photo-Z and weak lensing requirements. And I also put on this plot what would correspond to the SCOC phase 2 recommendation, and also what would correspond to a universal survey. So to go to an effective strategy, we need to define filter allocation, and this was given by the type 1a requirements for the UD fields and the calibration requirement from photo-Z and weak lensing, and we end up with a typical here survey where you have the number of visits as a function of the season for 3 type of field, for the UD fields at the top, for 2 other fields, and then the Euclid field, which are have a specific cadence requirements. And what you see here, this huge increase in the number of visits correspond to a higher number of visits per observing night corresponding to the UD fields. We have simulated this survey with very simple observing conditions, and we have defined metrics to assess these strategies. So you have the 3 metrics here for the photo-Z left, weak lensing middle, and type 1a supernovae on the right. It's for the Cosmos fields. Each of the points for these 2 plots here correspond to a strategy and to a filter. And for the photo-Z metric, it's simply the variation in co-added M5, which is, if it is bigger than 0, it means that the requirements are fulfilled. For the weak lensing metric, it's the ratio between the number of visits seen by the observing strategy divided by the number of visits corresponding to the requirement of the photo Z. And if it is bigger than 1, the requirements are fulfilled. And the type 1s supernovae metric is a little bit more complicated. It is more or less like a figure of merit, but it is a metric, so we called it the supernova metric of merit. And it can be defined per season, and it includes both the WFD and the DDF. And this is the result that we get, for instance, when we include a spectroscopic scenario for the redshift of the type 1a supernovae, but you see that you have differences between the strategies. So as a conclusion for this study, there are some promising scenarios, the deep rolling survey with 2 ultra deep fields and 3 deep fields. This seems promising, but this needs to be checked with realistic simulations using the LSTC scheduler. And the paper summarizing all these results is in review in desk. And I will finish with just one slide, which is we have also analyzed the V3 simulation with this new metric, this supernova metric of merit. And you have 2 plots here. On the left, you have the cumulative number of supernovae as a function of the year for baseline, so 3.0 to 3.3. And you see that with the baseline 3.3, we reach more than 1 million of type 1a supernovae after 10 years. And on the right, you have the supernova metric of merit as a function of the year for the WFD and DDFs. And you see also that you can disentangle, or you can see the difference between the 3 simulation from baseline 3.0 in black to baseline 3.3 in red. And I'm done. Thank you.
That's wonderful. It's great to see there are simulations improve science as time goes by. Let's take one quick question for these first 2 science collaboration. First hand that gets raised goes. I'm going to ask the following speakers to just keep it a little bit closer to their allotted time slot. We have some buffer, but not a ton. And if nobody has a question, I see some questions are being discussed on the comments and on Slack, so that's perfect. Let's move on to the next science collaboration, which is the transit and variable star science collaboration. Igor, you're on deck.
Okay, thank you, Fed. Can you see this slideshow?
Yes, no, actually it's still loading.
I can see correctly on my end.
On my end, it just says loading, so it's a black screen. Do you want to refresh? Try again?
Yep.
It came up there just at the end. I think it's just a matter of time.
How about now?
Go ahead. You're good.
Okay. So this is some quick feedback on behalf of the Transients and Variable Star Science collaboration. So what we noticed with the latest simulations available is that in general, there is pretty good improvement from most of the metrics. This is less pronounced an effect and a benefit for the study, for example, of periodic variables in our galaxy. As you can tell from the plot on the left, is the progression in the baseline strategy from the version 1 to the version 3.3 of the OPSIM. There is no significant improvement, although you see that we're clearly going in the right direction when it comes to cataclysmic variables and in general non-periodic variables that we can study in the time domain. I got some feedback by Steve who pointed out in particular that the rolling cadence can truly benefit those variables, those events that are not periodic. And definitely we can talk about compromising about the start date on the rolling if that's on the table. But I think many of us would kindly ask to please keep it that way or improve upon what's done so far. Because once again, we see numbers improving from 10 to 20% on average on most of our science cases. When it comes to microlensing, Natasha has done great work here, and I would give her the floor for commenting on this.
Yeah, so I'll do a summary of how the survey strategy is impacting microlensing. A lot of this was summarized in great detail by Jay Strader earlier today. So first off, footprint on the first order makes the most significant impact on microlensing. As you can see on the right-hand side, we have the retro footprint, where the high stellar density areas like the galactic plane and bulge and Magellanic clouds weren't included. And since including those areas, there's been over a 60% increase for across all different time scales and both detection and characterization for microlensing. In the baseline 3.0, which is all the way on the left on this plot, you can see at the bottom there's the detection metrics, which there's been some improvements in the detection as we've gone from just the galactic bulge region and now instead are looking throughout the plane. And you can see in the top left, though, those are the characterization metrics. And you can see there is a decrease by about 10 to 20% in the characterization efficiency. But when we've added the galactic plane, that allows us the new scientific, allows us to probe the population throughout the galactic plane. So there's that trade-off. And yes, thanks, Fed. So V3.3 is not included in this plot, but there's about a 20% improvement in the detection over V2.2, though note that the filter balance is not, there's a relatively rudimentary way of including the filter in the microlensing metric, and so more detailed metrics will be necessary for understanding that in depth. With regard to rolling, for the most part, for most microlensing events, overall rolling will decrease the characterization of microlensing events, but some sort of minor rolling like Jay was discussing earlier, which synergizes with Roman, where there's not too many observations taking away from the rest of the galactic bulge and plane, could be beneficial. And the work discussed here is in review in the app.js focus issue.
Okay, thank you, Natasha. So going real quick on the next topics, it's something positive that we notice is the increase on the metrics related to whatever is fast transient and extragalactic transients in general, and in particular, even when you consider both the preferred type of metrics chosen by the TVS science collaboration and, for example, by the desk science collaboration, there is good agreement that the baseline again improves in the order of 10 to 20%, if not more, for some cases. So kind of a summarize the feedback that we can offer so far is that we have significant improvement or stationary cases in most of the science cases relevant for TVS. This is not quite true when it comes to microlensing and characterization. So perhaps based on what Natasha said and what Jay said earlier today, perhaps we can think maybe of something different, something new, or even roll back on the plans, in particular for the bulge. We were a bit worried about the U-band lower throughput to affect in particular the ability to detect and characterize tidal disruption events, but the larger number of visits planned now kind of compensate for that effect, so we should be okay. And yeah, again, for when it comes to galactic plane, sounds like keeping the footprint as is or even improving it is definitely the preferred way to go. And I will leave you with a list of the papers that have been already reviewed and accepted in the special issue or in APJ led by TVS members, and point out some at the bottom that are now in the working or they have recently been accepted.
Thank you, Igor. Thank you, TVS. One quick question for TVS. If there are none, please continue the discussion on Slack and on the chat. And the next science collaboration on deck is the Galaxy Science Collaboration. Simona, are you ready?
Yeah. So I'm going to share my screen. And I realize that I don't have a share screen button. What is going on? Yes, there it is. Okay, good. Okay, so I'm going to share my screen and there we go. So this is in behalf of the Rubin Galaxy Science collaboration. We sent a message to everybody in the collaboration asking for comments or everything pertinent that was pertinent to this workshop. We didn't have any simulations or made by Galaxy members, at least we didn't have simulations that were sent to us, but more concerns and feedback to the SCOC. So first of all, we want to say that for Galaxy Science, we give a strong endorsement to the survey uniformity request by desk. For example, for the announcement of the uniformity at year 4 and 7. That is very important for both Galaxy detection and have complete samples on which we can work without having differences in photometric redshifts or errors in the magnitudes on the entire area for studies of galaxy clusters and detection and environmental studies. So that will be really will have a very negative impact on our science if the survey will not be uniform. The other concern that was expressed by members of the collaboration is the change in the filter coding, and particular the depth in the U-band is very important. On one end for IZ galaxies photometric redshifts and Milky Way studies, for example, for cataclysmic variables and other active sources, metallicity determination, reddening, etc. For example, I cannot. Okay, For example, we were wondering about the figure that was the analysis that was shown yesterday on the standard deviation of photometric redshifts, and you see that there is a peak in the standard deviation around redshift 2, and if the U-band depth is not very high, we think that this might be due to the Lyman alpha breaks that are missed by the fact that we cannot measure a correct color between the U-band and the radar bands. So the question that was asked to the chairs was if it would be possible to compensate this with longer exposures in the U-band. And for the estimation, they said around 50%. I'm not sure today we saw 30%, so probably we will have to make simulations to really understand what the improvement can be, not to lose this galaxy science. Another feedback was a concern about the dithering. So what will be the dither in the deep fields? In fact, to do low sulfur brightness science, we will need the dither of the order of the size of the larger objects in the fields. That means larger galaxies or galaxy clusters and groups that are there. And a large dithering will be useful to minimize the stray light from the light that is bouncing in the telescope and for building the sky flats. So to build the sky flats, we can use images that are not in the same area, and that is possible. However, the camera rotator will not be enough for the LBS science because we will have different illuminations of the camera at different angles. So it will be really difficult to make the right sky flats. And if the dithering is not large enough, the first bias, that is the stray light from the light bouncing in the telescope, cannot be eliminated in an efficient way to detect the very faint low super brightness structures around galaxy clusters and galaxies. So for example, what we want to detect are these very low super brightness structures. So these are for galaxies. And in a cluster, you see that the scale is much larger. And to detect the intercluster light, we will need large dithering so that the people doing low super brightness science can do their science. That is it. And as a general comment, as a collaboration chair, I would say another feedback for this calc would be perhaps to have more interactions with the chairs, not only by giving general information, but also perhaps discussing with us the implications of the plots and information that is given to, the documents. Because, for example, to create new metrics and really give a contribution to the SCOC work, we will need time and to discuss with the collaboration. So if we know it, in a short time from when you have the need, will be very useful. So we can work together on that. And that's it.
Thank you, Simona. If there is a question for a Galaxy Science collaboration, let me then, while I set up to show you the next presentation, which is a video, let me just add for the Galaxy Science collaboration, we announced, as I mentioned already, we announced the changes that we make, the decisions that we make, new simulations, anything that affects the survey strategy, both on community and via the science collaboration. And we're very happy to talk to the chairs as they need us to. So please pay attention to those announcements and then ask us questions via your liaison or directly afterwards. We're always very happy to talk to the chairs directly.
Thank you. That will be really useful. Sometimes, looking at the documents, we don't understand the implications or what would be needed from us. So perhaps expressing it directly, like, we really need you science collaborations to create new metrics. Just telling us directly would have been.
Yeah, we do. And I do think that your liaison, this is the role of the liaisons. And I think Louise has brought recently these concerns exactly about, for example, the response of the metric in different filters to the science collaboration. So we'll definitely work on making sure that the questions and responses get where they need to get.
Thank you.
Thank you, Simona. Let me then screen share. We have the next presentation is a video from the Strong Lens in Science collaboration. So let me screen share and let me share the audio of my system, which I never can find. I can never find that button. Just give me 1 second. Because I do need to share audio, share computer sound. I found it. So hopefully this works. If it doesn't work, I'll put it in the chat and I will fix it.
Hi everyone, my name is Nikki Arendse. I'm a postdoc at the Oscar Klein Center at Stockholm. Hi everyone, my name is Nikki Arendse. I'm a postdoc at the Oscar Klein Center at Stockholm University. And I want to give a short update about the impact of the LSST observing strategy on detecting strongly lensed type 1a supernovae. So first of all, I want to really thank the organizers for allowing me to send this in remotely because I couldn't attend the meeting. So thanks a lot for that. So the motivation here is that we heard these predictions of detecting lensed supernovae with LSST, where the numbers are really incredible, really orders of magnitudes more than the sample we currently have, which is just a handful. But we wondered what the numbers would be if we would apply the exact observing strategy to these predictions, and also what the properties would be of the remaining sample. So in this desk project, we investigated this further. We didn't only look at the observing strategy, but we only went into looked into questions like, what is the impact of microlensing of stars in the lens galaxy? Can we measure time delays from only LSST data? answer is not really. What is the feasibility for follow-up observations, and how can we distinguish lensed and unlensed type 1a supernovae? So for this, we simulated lensed type 1a supernova light curves, including microlensing, and then we applied the simulated cadence using the OBSIM database. So here we use the V3.0 observing strategy, which now, of course, there's the V3.3, where the main differences are the coating of the mirrors, which leads to a different sensitivity in the different bands. But the sensitivity in the U band is decreased and all the other bands are increased, which for our science case is actually really good because lens supernovae are high redshift, so they're red. So we only look at the G to the I bands anyway, and those will have a higher sensitivity. So that will even make our results a little bit more optimistic. So what we present here is a little bit of a conservative estimate. So first of all, we looked at the question, how many lens type 1a supernova detections remain when we apply this exact observing strategy instead of only looking at the peak magnitudes. And we find that per year, we expect around 44 lens type 1a supernovae. Which is really great compared to what we currently have. For ongoing surveys, this estimate is really orders of magnitudes lower. But then if we want to do cosmology with these lensed supernovae, we also need them to have large enough time delays to get a good relative precision on the time delay measurement. And if we only look at systems that have time delays larger than 10 days, we still expect to find around 26, which is great. So then we looked at the impact of the rolling cadence on lens supernovae. So the rolling cadence is very good for normal supernovae because you will have slightly lower number of supernovae, but the ones that you will find in the active regions will have a much better sampling of the light curves. And because there are so many supernovae that we expect to find, it makes sense to compromise a bit on numbers and go for higher quality. But with lens supernovae, this is not so clear because they are much rarer. And in previous implementations of the rolling cadence, this has led to really missing out the majority of the lens supernovae because you don't sample the background regions enough, so you miss a lot there. So we wanted to see what it was like with the current implementation. And on the left, you see the histogram of the number of detections per lens supernova for the non-rolling and rolling cadence. And you see that compared to the non-rolling, the rolling cadence has a larger number of systems with low number of detections, but also this tail going to a high number of detections. So you both get systems with fewer and more detections. And then on the right, we plot the expected number count per year of lens supernovae when you require a certain limit of detections. So if you only require a few detections, then you see that a non-rolling cadence will find more lens supernovae. But when you want to have 20 detections or more, then actually the rolling cadence wins out, because even though it discovers fewer objects, the ones that you find have a better sampling. So the conclusions here are that non-rolling will find a bit more lens supernovae, but rolling will have better light curve sampling. But I also want to emphasize that this difference is not extreme. So non-rolling will find around 50 per year and rolling for around 44. So it's good news because it means that the rolling cadence is definitely not detrimental to the lens supernova case. And in fact, it can also be good to have a few of those 44 that have more high quality light curves. Then another question that we want to look into is if we expect to find lens type 1a supernovae in the deep drilling fields. This would be amazing because then you would have you would discover more fainter objects and also have much better light curve sampling. So yeah, we computed with our simulations what we found in the deep drilling fields. And the answer is we expect to find around 0.2 per year. So this is because the area is so small. So if they go off in the deep drilling fields, we're very likely to find them. But because lens supernovae are so rare, we just don't expect many to occur there. Which is a shame because it would be great to have them there. Of course, it's not impossible. So especially over the full 10-year duration, we can still find a few. So we should still look out for those. Another thing we looked at is the feasibility of follow-up observations. So for this, we required a subsample that not only had large enough time delays, but but was also detected early enough, so at least 5 detections before maximum, and bright enough for follow-up, because the very faint objects that we will find with LSST, it might be very difficult to get follow-up resources to classify them. So when we applied these cuts to our sample, we were still left with around 10 objects per year. And if we assume some uncertainties in the mass model and the time delay from literature, then this could lead us to a 1.5% precision H0 measurement in 3 years of LSST observations, which is really good for such a newly emergent probe. So to summarize, we looked at the feasibility of detecting strongly lensed type 1a supernovae with LSST, and we expect to find around 44 per year for the non-rolling cadence or 50 for the rolling cadence. And a subset of those will also allow us to constrain the Hubble constant to 1.5% precision in 3 years. We also looked at the deep drilling fields and sadly don't expect to find many there, but not completely impossible. So that was my short update. If you have any questions, please feel free to message me on Slack, Nikki Arendse, or send me an email at this email address. And yeah, looking forward to hear if you have any comments or other ideas. And again, very sorry that I couldn't attend the meeting in person, but looking forward to see the recordings. Okay, thank you so much. Bye-bye.
Let's send a thoughtful thank you to Nikki for the wonderful presentation as delivered asynchronously. We do have people from the from the Strong Lens in Science collaboration here if there is a question, but also you can address them to Nikki and to everybody on the workshop on Slack and in the chat. I think the next science collaboration on deck is the AGN science collaboration, if I'm not mistaken, and that would be Neil Brent. There you are.
Hi. Can everybody see that okay and hear me?
Yeah, it looks good and we hear you good.
Great, thanks. Yes, so today I'd like to briefly summarize the overall Cadence inputs coming from the AGN science collaboration and also emphasize a couple of specific issues. I'm going to give sort of an overview and talk about the deep drilling fields, and then Roberto Asaf has kindly agreed to present some considerations relevant to AGN photometric redshifts. So in the AGN science collaboration, clearly we're interested in the cadence from the perspective of variability of the many components of AGNs, ranging from the accretion disk to the line emitting region, to the obscuring materials, to the relativistic jets, and all of these vary in fascinating ways on a variety of timescales. And then, of course, we're also interested in ensuring that the cadence approach will perform superbly regarding AGN selection and AGN characterization, including, for example, photometric redshifts. So the AGN science collaboration has been working on cadence issues for quite a while. We have delivered 8 cadence notes in addition to the 2018 white papers, as well as 4 coded metrics as part of that. Here are the abstracts from 6 of the 8 cadence notes. These cover topics including photometric redshifts, recommendations for the deep drilling fields, AGN variability metrics, blazar variability, relativistic jets there, structure function metrics, as well as utilizing differential chromatic refraction to refine AGN redshifts. And we think that with good choices for the cadence, all of these things can be executed very well. Furthermore, there are 3 journal articles detailing many of the detailed considerations. Here are the abstracts for these, including, again, on blazar variability, on accretion disk reverberation mapping that lets you measure the structure of accretion disks by looking at interband lags in the continuum, as well as by looking to measure emission line reverberation just using photometric bands, which one can do in a broad statistical sense, even just with the photometric coverage of Rubin. So I refer you to all of those for many of the detailed considerations. We also have, of course, continued to communicate with the SCOC via community input opportunities, via feedback to our SCOC liaison in the AGN Science Collaboration, Franz Bauer, and then regularly at AGN community meetings, we highlight the need to give us inputs broadly across the AGN community, even if you're not a member of the AGN Science Collaboration, to ensure that good feedback and all the best ideas are being captured. Furthermore, we do continue to work through the operation simulations to assess if and how these allow desired AGN science to be achieved. And we also have attempted regularly to coordinate with other science collaborations, for example, the Dark Energy Science Collaboration, to see if we can push for mutually acceptable Cadence solutions that allow great, for example, supernova science and great AGN science without either of those being, too badly compromised. And then I will also just say briefly that if you want to see much more discussion of Cadence issues, we do have about 25 hours now of science talks and discussions on YouTube from our annual summer meetings. Clearly, that might be too much to digest all in one go, but we're happy to point you to the specific presentations within there that address Cadence issues that might be of interest to you. There is quite a bit valuable in there, and some of us have attended all the meetings and kept a bunch of notes and can point people to the things that are most relevant. Okay, so then I want to move on to a couple of specific issues with the remaining time. One thing that we have done is we have done quite a bit of work on the deep drilling fields and what will allow great AGN science in the deep drilling fields. And here I will point out, of course, that the AGN Science Collaboration, has been a leader in gathering multi-wavelength data for the deep drilling fields, including very extensive Spitzer data led by Mark Lacey and colleagues, including very extensive observations in the X-ray band with XMM Newton, led by my group, as well as doing a broadband SED fitting for the purposes of AGN selection and characterization and so on. There's a large number of published papers there that we think will be very valuable once the Rubin switches on for actually studying AGNs as well as all the other sources. And so please keep those in mind and check those out. Here, what I have on these two slides are a set of 10 essential inputs that we sort of have distilled from the white papers the AGN Science Collaboration has prepared on the deep drilling field. I'm not going to cover all 10 of these here, given the limited time. I'm just going to cover the ones that I've highlighted, and I've posted all 10 of these in the Slack and distributed them regularly to anyone who will be willing to listen to me. A couple of key points. First of all, given all of the multi-wavelength data that have been gathered, it is quite important to ensure that the Rubin pointing positions are optimally chosen to align with all of those multi-wavelength data, which represent very intensive investments of often very expensive observatory time. And so we actually suggest specific pointing positions, which we still think are very good choices. And we've continued to sort of operate under the idea that those are going to be the pointing positions for the purpose of allowing us to gather sort of precursor multi-wavelength data. Another one that I want to emphasize here is that, given the need to monitor AGNs over long time scales for reverberation mapping purposes and so on, one wants to minimize the seasonal gaps and thus have the DDF observations extending over the longest possible observing seasons, pushing like 7 to 8.5 months, whatever is possible. Now, we understand that leads to, challenges of very large air masses late in the season and so on. And so we have suggested a so-called accordion cadence approach, where the deep drilling field observations are more densely packed in the central part of the season, where observing conditions are more favorable, and then are progressively less densely packed as you go out toward the edges of the season, kind of like the bellows of an accordion, which can sometimes be densely packed in the middle and less densely packed as you go out. And this has been suggested to provide good total DDF depths because you gather more observations during the central parts of the season. It also allows you to provide suitable dense coverage over a fairly long time span, about 2.5 months or so, we think is probably necessary to perform effective AGN accretion disk reverberation mapping, which we suggest would benefit from essentially nightly observations in the central part of each season. And then also, this approach would also allow effective complementing of spectroscopic broadline region reverberation mapping, which is ongoing in these fields and will continue ongoing through the Rubin observations. And then finally, the final one I want to emphasize, this one in red here, is that if needed, due to time constraints, if needed, a reduced number of 4 years of dense deep drilling field monitoring could be implemented following specific details that we outlined in this cadence note, while still ensuring long observing seasons for all 10 years. So in other words, 4 of the 10 years would have more intensive observations than the remaining 6. And those 4 years could be strategically toggled across the various deep drilling fields to reduce any instantaneous Rubin observing demands and allow overall scheduling flexibility. I believe the Dark Energy Science Collaboration has proposed a broadly similar idea, which I think they call rolling deep drilling fields. And I think something like that could be very beneficial, perhaps, to both science collaborations. And I hope these points will be considered, the ones I've highlighted as well as the others. And with that, since time is limited, I would like to pass speaking on to Roberto Asaf, who has some useful information to share on AGN photometric redshifts. Please go ahead, Roberto.
Thank you very much, Neil. Yeah, so this is actually very much in line with what Simona and Jeff have been mentioning for galaxies, but so deep Rubin is actually quite important for photo Cs of AGN, particularly when they're breaking the whether you have the Lyman break or not. But for AGN, they're particularly more important. I would say it's more important just because we don't really have many features in the SED. So this is a plot that was made by Mara Salvato and Raphael Shirley looking at photo Cs in the EFETS field of AGN, using U-band on the left and not using U-band on the right. And you can see that U-band actually does have a significant effect in terms of the number of outliers as well as on the dispersion. Also, U-band is important for the gradient identification as it widens the wavelength range in which we get to map the SED, but also U-band has higher variability than the other bands. Probably not as important as for photo Cs, we can still tell when, to some extent, when objects are AGN without being able to measure the photo C, but still something important. So whether the changes are critical, the way I think about it is U-band was already a mag shallower in the before 3.3, and now the difference has increased a bit. So it's taking something that was far from ideal to actually and just making it a bit worse. This will affect things like studies of the feign end of the AGN luminosity function, of course, but also cutting out being able to tell whether objects are AGN or not at faint magnitudes might actually also affect things for other SCs, and I think people need to be thinking about that as well. In terms of the potential mitigation strategies that have been discussed, I think more visits are a really good thing because it will also give us more information on variability, helping with the selection and also with the photo CISA as well. And of course, deeper co-added U-band will just help with the accuracy of photo Cs. So that was all. Thank you very much.
Excellent. Is this the last slide for AGN?
Yes, it is. Yeah, we're good now. Thank you. Yes.
Good. Thank you. Thank you. Maybe one question before we pass on to the last science collaboration that we'll speak, which is Stars Milky Way and local volume science collaboration. There's also discussions ongoing in the chat. I think there's a question for the speakers. So just please keep an eye on the chat and on the Slack. I think the question is on the chat, not on the Slack in this case.
I'm sorry, I haven't been able to look at the. Am I supposed to address something in the chat or?
Yeah, well, you can do that asynchronously. I think John had a question.
Okay.
I'm not sure who the question was for. Also, to everybody, what you're saying in the chat, I know you cannot copy and paste the chat. That's the University of Delaware policy on chats on Zoom. But I'm saving all the comments and everything that is being said on the chat in the Google Docs that has the notes. So your comments are not lost. They will be saved in perpetuity. And I don't see any hands raised, so I would like to pass the microphone to Will Clarkson, if you're ready, for the Stars Milky Way local volume science collaboration. And this is our last community contribution.
Okay, can you all hear me, and can you see the slides? Good. Okay, I'll try and keep this short because I know we're running low on time. So thank you, Fed. Thanks, everyone. There's been an entire talk on the Milky Way task force by Jay Strader earlier on today, so I'm not going to talk much about that. But I do refer you to Jay's slides on this, except to say that there's been a huge improvement just of first order from the earlier versions of the strategy, even to the most recent versions that you see here in these two pictures showing coverage from Jay's presentation. So thank you to everyone who's worked on that, both on the project side and the community. So Stars Milky Local Volume has a hugely diverse range of science cases, stars, the galaxy, and the local volume. And as you might expect, there's been lots of diverse efforts to try to constrain how well the observing strategies will work for this science. Here are some of them that SMWLV members have either contributed to or led, all the way from recovering brown dwarfs locally to local group dwarf galaxy light curve recoveries. As far as I know, most of these have not yet been updated for the version 3 of the baseline, so I don't have an update for version 3, but this gives a good idea of some of the efforts. Following discussion, I think I heard earlier this week, though, I'll focus my few minutes of fame on some of the gaps I think we've been hearing about. And this is really to those who are watching this talk, either live or afterwards, who might want to contribute to this. There's lots of areas that I think we still want a contribution in. Just to repeat very briefly from Jay's talk today, metrics are still needed for issues of, for example, filter balance and visit distribution for the inner plane, as well as for the full sort of bulge plane region, and also for sort of how well we should cover Roman survey regions as those become better defined. So just to repeat what Jay said, I think this morning, input's needed on this. But in terms of some of the areas of ongoing need, we heard a little bit about, I think, Halo science. There are some metrics in progress to address how well version 3 and beyond will work for Halo science. Just to highlight one of those, Fabio Ragosta has been leading a project to determine how well LSST can detect sort of new populations, both photometrically and kinematically outside the plane. There are a lot of science cases that you see given in, for example, the science book, that I think still need some development into actual figures of merit for the science. And I think one thing we'd like to know in the collaboration is, for example, what is the current state of, for example, star-galaxy separation metrics? How do those flow through from observing strategies? And so, what is the impact of strategy in the U-band? A lot of this, it seems to scale. You can sort of see how the scaling might work with things like depth, but we still need metrics for this. So to echo, I think Lynn mentioned this earlier. I think we do still need metrics for these. Metallicity determination, I think, came up earlier in the week. We did get as far as producing a notebook that does a science figure of merit for metallicity precision for clump giants, based on U minus I d-Redden photometry. And that's got to the stage of actually having a figure of merit in terms of what volume is probed to a particular precision. So that should be revisited, and we would like to work with the Sims math team to do this. Other figures of merit I don't think we have yet have to do with main sequence metallicity sensitivity from colors, and then there must be some R library based work on variability based figures of merit, but we don't know how far that's progressed yet. So that's also an area that would be good to update. Slightly more broadly, there must be some stellar cases that we're currently missing as well. For example, are there any extreme color objects that should be followed up? Every so often at a conference, somebody will mention a class of rare objects that one might expect to see one of these per enormous area on the sky that something like LSST should be good for. And so there is still, I think, some low-hanging fruit out there for science cases that build figures from these existing metrics that the Sims math team and community have produced. And then another recent effort of SMWLV is star cluster science. The star clusters working group within Stars Milky Local Volume has recently been revitalized, and the link in the slide here takes you to the science roadmap for this group. So there must be some metrics, again, that could be straightforwardly developed to help optimize, to help understand the return for science from observing strategy for star clusters. And then rumbling along in the background is astrometry. This has always been something that SMWLV has raised concerns about, to do with, it's almost a level above the metrics themselves, to do with how well will LSST actually deliver proper motion and absolute astrometry and parallax, in terms of sort of how well will the observations allow that reference frame to be built from Gaia. Are there places where Gaia itself doesn't perhaps work so well? In particular, what happens if it turns out that LSST does under-deliver in terms of its astrometric precision? What will be the chances to improve things? Will there be engineering time? Or will the plan be that everything gets calibrated from the main survey data all the way through? So that'd be nice to clarify. And just while I have 1 minute, just to finish up, in terms of sort of solidifying science, just to advertise quickly, there is a workshop on ultra cool dwarfs in the solar neighborhood that John Geesis is going to be running next week. I flashed the link here on the slide. I can put it into the chat afterwards if anyone's interested. Yeah, this is all issues that we need input on. So if you have any interest in working on this, please contact Peregrine McGeehee or Kristen Daig, who are the co-chairs of SMWLV, and I'm sure you'll get a receptive audience. Thanks, Fed.
Fantastic. Thank you very much. Is there a question for Stars Milky Way local volume? Let me echo something that you said. I put it in the chat as well, we are actively seeking to monitor the halo science, the impact of U-band changes in the halo science. We know that that is one of the areas that might be impacted. So if anybody has scientific insight or coding insight and can help create a metric for that, please reach out. We definitely want that metric, as we want metrics to better understand the impact that these changes have on PhotoZ, as was mentioned by many of the earlier science collaborations. We do have PhotoZ metrics. I see that there is a bit of a discussion that I hope will continue on Slack about that. We need to understand the relative merit of improving PhotoZ slightly at low redshifts versus higher scatter, higher standard deviation on PhotoZ at redshift circa 2. So we actively look for scientific insight and help interpreting those results. Are there any comments? We are 2 minutes to the end. Anybody has something like a burning desire to add something to the conversation at this moment? If not, then let me just remind you of one more time, the last time, I promise. Let me just remind you of the way in which you keep up with the SCOC and deal with the work on survey cadence. The SCOC meets roughly monthly. We have liaisons in each of the science collaborations. It is their job to communicate with the science collaboration. Here, the science collaboration concerns them, bring them to the SCOC. Here, the SCOC suggestions and needs and bring them to the science collaboration. I want to thank all the SCOC members, because that in and of itself is a hard job and a significant service commitment, and they do that on top of all the work they do in achieving these very hard to achieve optimization over the entire scientific landscape of this complex survey strategy. We also have office hours, so we would love to see you there. They've not been attended very much. Please keep an eye on community for possible changes of time slot, but at the moment they happen on the last Monday of the month at 7 a.m. Pacific time or Rubin time. We encourage you to keep up with the SCOC on community. You can subscribe to the topic survey strategy and then get all the updates about survey strategy related questions and topics right in your email, or just keep an eye on updates on the topic directly on the community.lsst.org website. We hold these workshops annually, so we hope to see you again next year. We are present at many other Rubin workshops talking about survey strategy. We always have a session at the PCW, and at this next PCW, in that session, we plan to present the phase 3 recommendation of the SCOC, which will bring us to the beginning of the LSST survey. So please stay in touch with us, leading to that and leading to the release of the report in late September. And finally, a lot of what we talked about depends on metrics. I do have a slide on the metrics. The metric analysis framework is a Python framework to write science cases that get evaluated against the survey strategy. If you're familiar with it, you probably also know that we have a wealth of tutorials on how to write new metric or look at the old metrics on GitHub. But if you're new to it, we always are happy to support the inclusion of new people. We are planning on posting a video tutorial on the math, which will include, updates on the most recent version of math and a brief how-to on how to build metrics, and also the survey strategy team has been generously supporting the community in writing new metrics over time. There's a possibility of setting up office hours for them if we have a high request of support for building the metrics that we might be missing for science. And that's all I had. I want to thank everybody that attended the workshop. Please continue talking on the Slack channel for the workshop and continue talking to the SCOC. And I hope to see you again soon at the PCW, at the community workshop, if not earlier. Thanks, everybody.
Thank you.
Thank you. Bye.
I guess UD Zoom works all right
Yeah,
for holding meetings.
oh, yeah. Oh, I didn't even worry. That's right. Maybe I was approaching the limit, wasn't I?
I'm going unplanned next. I've never done a breakout room.